For many decades, software security has been a focal point in ensuring that our applications, programs are executed correctly, ethically, and intentionally. Day by day, there are state actors, hackers, adversaries, you name them, cracking the underlying infrastructure of many software programs, applications, and components. These hackers will find newer, more intricate methods in avoiding detection and making intrusions on software. Hello, everyone. My name is Joseph Long, and I'm here to discuss control flow integrity. This research topic is written by researchers from the computer science departments of the University of California and Princeton Universities, along with researchers from Microsoft. After reviewing the paper, I would comment on that control flow integrity being the most effective present-day security measure to counteract modern-day exploits. Now, without further delay, let's get into discussing this application. Within this presentation, there will be three distinct main areas or subjects that I will be conveying to persuade the idea of implementing control flow integrity. These pillars being the background, core concepts, and implementation and applications of control flow integrity. All of these contents can be referenced within the paper. Background. Why was control flow integrity developed and how it's incorporated into the landscape of software and even maybe hardware security. Next, for core concepts, I'll explain what control flow integrity is and the main takeaways from it. And then in the last section, I'll explain some real examples along with its performance impacts and how it's used with other security capabilities, that being control flow integrity. Now, before delving into the amazing capabilities of control flow integrity, let's evaluate the background and the historical context of it. Furthermore, giving a basis of why we would need this technology at all. Software vulnerabilities history. Attackers have been inputting their own malicious code on pre-existing software application. This is known as code injection. Some notable examples include cross-site scripting attacks and SQL injections. This attack has been around since the 1990s. Return-oriented programming. This is a malicious exploit that allows an attacker to run a script in the presence of security defenses. This was in response to attackers being unable to run code within data memory. This attack has been around since the 2000s. Last but not least is buffer overflow. This occurs when a program writes to memory more than is capable of being written to, which can cause issues within memory. This enables adversaries to change return addresses and intercept the execution flows. This attack has been around since the 1980s, and one of the most famous attacks was the Morris worm, which infected a Unix server, which quickly spread across other computers, essentially causing major shutdowns. Now let's discuss some modern day security implementations to combat said exploits. Stack canaries. Essentially, stack canaries are small security indicators placed on the stack before a return address to detect buffer overflow attacks. When a function is called, a value is placed between a local variable and the return address on the stack. Before returning from a function, a check is placed on the canary value. If an overflow attempt modifies the return address, the canary value is also altered, triggering a security violation and terminating the execution as soon as possible. Next is runtime elimination. This is a technique that detects and prevents buffer overflows dynamically at program execution rather than just during compilation, essentially ensuring that the memory access induced by the program stays within bounds. Next is randomization and artificial heterogeneity. Essentially, this is a security technique that will randomize the address of the stack in the memory at runtime and change instruction layouts across software instances. So, what does that mean for us? This makes it extremely difficult for attackers to predict memory addresses. Next is tainting of suspect data. Taint analysis tracks untrusted data, such as a user input, through a program and prevents it from influencing security critical operations. When user input is received, it is marked as tainted. The tainted data becomes closely monitored as it moves through execution. If tainted data reaches a dangerous function, such as a system call or memory write, the execution will pause. Now let's glance at some common questions you may all have. With these security measures in place, why bother with more security measures? Well, attackers develop and modify their attack strategy and start attacking it as soon as possible. For example, in stack canaries, adversaries were able to leak canary values and overwrite pointers instead of the return addresses, essentially circumventing the security measure. Now, how would control flow integrity help? That's what I'll be getting to in the next section. With today's security code features, control flow is a lot easier to manipulate than directly executing their own code. No need for payloads and no need to change existing code. While the security tools discussed do not fully prevent such control flow attacks, control flow integrity will. In this section, we will discuss the necessary components. Control flow, the purpose of control flow integrity, implementation, enforcement, experimentation, and lastly, a big section, security benefits, performance, and practicality. So what is control flow? Well, control flow refers to which the order that individual instructions, statements, or function calls are executed within a program. It determines how a program progresses based on logic, loops, and function calls, and also conditional branches. Some key concepts also include programming, sequential execution, conditional branching, and most importantly here, function calls and returns, and indirect branching. Now, control flow integrity is a security mechanism that ensures a program's execution follows a predefined set of valid execution paths, also known as control flow graph. The main focus of control flow integrity is to prevent attackers from getting access to executions by enforcing strict control over where a program can transfer execution, like jump commands in machine code. Constraining control flow isn't new, especially in security purposes. Much of the hardware out there have been able to prevent data memory execution so far. Execution can only follow valid paths, though, in a pre-computed control flow graph. Control flow integrity stops the attacks that alter control flow, such as return-oriented programming and jump to libc attacks. Now, speaking of control flow graph, a very important core component of control flow integrity. Let's briefly discuss it. So what's the idea behind control flow graph? Well, first, it maps out all the possible execution paths within a program. This is created prior to execution. And secondly, this is created prior to execution using static binary analysis and code analysis. In other words, examining the binary code of a program to find any security vulnerabilities without actually executing the program. You can think of control flow graph like our everyday traffic system. When you're driving, the roads your car is on can represent the control flow paths or the function calls. And the traffic systems, such as stoplights, yield signs, stop signs, will be seen as valid transitions in the control flow graph. Control flow integrity works by inserting runtime checks that validate control flow transitions through machine code rewrite. Each indirect control flow instruction, such as a function call, return, or jump, is paired with a security check. ID labels are embedded at valid jump destinations. Now, executing an indirect jump, the system verifies that the destination has valid label. If the destination is invalid, execution is canceled as soon as possible. But in order for control flow integrity to work, assumptions must be made. There are two items. One, non-writable executable or non-writable code. Attackers cannot modify code memory. And two, executable code. Attackers cannot execute injected data as code. In the end, if every indirect jump has a check, adversaries will be unable to infiltrate and execute their motive. Now, this is the general overview of the implementation. It starts with binary writing using a tool. These binary writings are implied on existing binaries on the program executables. And then lastly, inserting ID labels at valid transitions. Now I want to talk about the experimentations that the authors did within the paper. The authors experimented using spec computation benchmarks. For those who are unfamiliar with spec computation benchmarks, it stands for Standard Performance Evaluation and Corporation, meaning these tests are used to evaluate the computer system's performance in executions such as integer calculations and or math and science calculations. Certain programs were compiled and tested with full optimization. The parameters for each program had a control flow graph and a control flow implementation of 10 seconds. All of this was occurring on the x86 architecture. The authors performed binary rewriting with Vulkan, native to the Windows OS, to modify the executables. The key thing is no need for access within source code. Following the implementation we discussed before and the assumptions, the authors were able to calculate the overhead. Here, I wanted to discuss the benchmarks and measurements. The figures you see shows a normalized overhead when using control flow integrity. Some of the programs was ranged at 0, and some of them even to as close as 45%. But overall, the overhead was 16%, which, according to the authors of the paper, it was considered tolerable. Now, what benefits can be of use from control flow integrity? Well, it can prevent common exploits such as jump to libc attacks, return-oriented programming, and buffer overflow attacks. It will not and should not require any source code access and will be utilized with any existing binaries. It has compatibility with commodity systems, which is a system built using standard available computer components. And lastly, control flow integrity provides little to no performance degradation on performance. Overall, making control flow integrity a practical and effective security countermeasure to hackers. Well, you're probably telling me this sounds too good to be true. And you're right. Every implementation always has its setbacks and cons as well. Now, since control flow integrity has to be done static analysis right before its execution, it does require more overhead for dynamic code. In other words, extra time to verify, which can cause some issues. Next, if an adversary was able to infiltrate a valid control flow graph, there wouldn't be a way to detect and stop them. And next is the security and performance trade-off. The more detailed and intricate the control flow graph becomes, there will be an increased overhead when control flow integrity is implemented and executed. Now let's pause and ask some questions that you guys may have. What is the significance of the jump to libc attacks? Since I briefly touched on them. Sourcing from online resources describing this attack. It's an attack that begins with buffer overflow, in which with its execution, the return address on a call stack is changed with another execution present in the process. What can result from this? Hackers are now able to call shellcode and execute their own code. And the next question is, what is the baseline for overhead? Well, this is dependent on each system and programs and the people working on them to be considered what is an acceptable overhead. Well, for control flow integrity in this case, the authors described it as tolerable. They also discussed the possibility of optimization, but not have covered it in the paper. But they believe it should reduce the overhead even more without compromising the control flow integrity's trustworthiness. The authors have deliberated further that it's on par or superior with other techniques to mitigate the security flaws. Now, the important part is its critical role in strengthening many of our already present real-world applications. Inline reference monitors, software fault isolations, software memory access control, and shadow stack call. Inline reference monitors are techniques that automatically insert security checks into the program's binary, which usually occur at runtime. Control flow integrity in this case ensures that attackers cannot override these security checks through valid pathing of the control flow graph. As a result, access controls are strengthened and won't allow any actions that are unknown to the program, such as authorizing privileged system calls. Software fault isolation. The purpose of software fault isolations is to deter unsafe memory access through isolation in the program. The role of control flow integrity here is to rid unnecessary checks in memory. Software fault isolations in general are used for sandboxing, which is better for scalability and efficiency. The result being a reduced overhead using software fault isolations. Next, we have software memory access control. Now, software memory access control are built on top of software fault isolations. allowing access control within the function level. Control flow integrity ensures only certain execution paths can see sensitive data or not. For example, if there is a confidential information a company needs to store into memory, a software memory access control can ensure that specific parts of the program can perform read or write into specific memory locations. Control flow integrity here will again not allow adversaries to perform certain actions to jump to these memory locations using storing confidential information. Now, lastly, we have the shadow stack call. A big challenge within control flow integrity is preventing return-oriented programming attacks. It's difficult to track the return addresses of these function calls. Shadow call stack stores return addresses as separated protected entities. Shadow call stacks ensures the returns are to the right location. Another amazing feature is that control flow integrity can reduce the overhead of this implementation between 729% to 1900% to a mere 21% according to the authors of the paper. A huge advance in preventing return-oriented programming. Now, how do we know that control flow integrity is a valid technique? One of the interesting facts about control flow integrity that it can be proven mathematically. And there is a model in the paper describing that it can defend even the deadliest adversaries through math. This gives great reassurance that control flow integrity cannot be deviated from control flow graphs, resulting a trustworthy security technique. To wrap this somewhat of a short, brief introduction to control flow integrity, control flow integrity is more than just a security technique. It's an essential component for enhancing the really pre-existing security techniques. From what we've seen and discussed, control flow integrity strengthens inline reference monitors and software fault isolations. It also enhances memory protections through security memory access control, and also the protected shadow call stack, which helps stops return-oriented programming attacks and ensures security function returns. It also has mathematical proof that it will be correct, ensuring its effectiveness against powerful hackers. Overall, proven to be efficient and highly effective against modern software exploits. Now for your questions. Will, in the future, control flow integrity be implemented in dynamic environments? Well, actually, control flow integrity is currently being executed in a static state prior to program's execution, essentially static analysis of the binary files. What will eventually happen is that there will be an increase of overhead in performing of control flow integrity in a dynamic environment. As a result, longer runtimes and when it would be feasible to do so. But there is research on the capabilities of dynamic control flow integrity using lockdown on the 86 architecture within Linux. Now, will control flow attacks remain a problem? Yes, hackers will find newer ways every day to circumvent the current existing security mechanism. So the need for innovating new techniques, specifically computer security techniques to defend hackers, will always be needed. Any outside organization has utilized this security mechanism? Yes, many companies have already adopted this model. Though it wasn't present in the paper, there are many sources online stating they've been using it. For example, Microsoft has a program called Control Flow Guard and the Return Flow Guard, utilizing control flow integrity. Thank you for listening to my control flow integrity presentation.